song is about modifying gravitational lensing from massive gravitons.
Thank you for coming out. So, as Neil said, I'm going to be talking about massive gravitons. But as with any time when you talk about some theory of gravity other than GR, and the audience is anybody but people who already work on that, and everyone, the usual response of the audience is to say, why would you mass this beautiful theory? We like GR is beautiful, wonderful, it's worked for so long. What's the matter with your theory, people? Why can't you just leave all off? But I think the generic answer to that is lambda, the current acceleration of the universe, which no sane person studying GR, I think, would have put in. That's not fair. But nobody really expected or wanted to find in the actual universe, which is this strange fact that the universe's expansion rate is accelerating. It's not really something you would want. Especially, you wouldn't want it at the crazy level, crazy tiny numbers that we find in nature. So we have this severe problem, which is that the dominant form of energy density in the universe today is of a form that's uncalculably small, and yet is dominating the future of the universe. And I mean, this is obviously driven many people to embrace multiverse theories, where our universe is only one of like a nearly infinite variety of universes, and we just, and then you use anthropic selection, you get down to this small value. But I think that given that this problem has driven many very qualified and people to embrace many universe explanations, I think that if that's one of the alternatives, then messing with GR is a completely viable alternative compared to that. So if you don't find the cosmological constant to be disturbing or the dark energy to be disturbing, then obviously you can be turned off by both of these approaches. But if you're willing to say that theory is going to make any progress on why the cosmological constant is small, then I think you have to be willing to consider modified gravity at least at the same level as infinite number of universes, most of which we can't find out anything about without. So that's my little spiel justifying my existence today. And so that said, even though the cosmological constant was only found recently, the modification of gravity I'm talking about actually has an extremely long pedigree. And so back in 1939, these two guys, this one's a little bit better known, Wolfgang Pauli and his student Marcus Spitz, asked the question of, so in GR, the graviton is massless. So the force carrier of gravity, the linearized perturbations of general relativity, gravitational waves, no mass. So they're just two tensors, and that's all. And so what these guys asked was, well, what do you have to do if you want there to be associate a mass to the graviton? And so they found out that at the linearized level, so this, h mu nu equation of motion for a graviton, if you want to put a mass into that equation, there's a unique way to do it at first order in perturbation theory that doesn't have a severe form. It's only one way to do it, which is kind of an interesting statement. So if you want to extend gravity to having a mass, you don't actually have very little theoretical freedom in how you go about doing that. And what happens when you do that is that, as I said, GR is in fact the unique theory of a spin-2 particle, massless particle. But whenever you move away from that theory by adding a mass, you also turn on more degrees of freedom in the graviton, because it's a spin-2 particle, so you spin from 2, 1, 0 to 1, 2, and that kind of progression particles in spin. And so in gravity, there are invincible vectors and scalars, but they're non-propagating degrees of freedom. So, like we all know in early universe stuff, the vectors all decay in GR because there's no propagating vector degree of freedom, etc. But once the graviton has a mass, then all bets are off. All of those degrees of freedom become real degrees of freedom that are vested with, that are propagated. So the real particle associated with the vectors and a real particle associated with the scalar degree of freedom. And so it turns out that whenever you so whenever you do this, the vectors actually are boring. They don't couple to anything. They're propagating degrees of freedom, but they don't propagate anything. And so you can kind of ignore them. And you can focus on the scalar part of the graviton. And so, taking gravity and adding a scalar is a very old game too, going back to random thinking. But it turns out what I'm going to be talking about today is really a theory where focusing on a theory where there's a scalar part of gravity in GR. It's a straightforward extension of GR, but where you're very bound by theoretical rules about how this scalar can behave. There's not just a freewheeling theory where you just throw anything in, but a very particular set of rules where you have to be consistent theoretically. And so that's actually going to constrain things quite a lot. It also make things interesting. So you might say, you started by talking about the cosmological constant, and now you're talking about mass of gravity. Why would these be related, other than that maybe you're using cosmological constant as just a crutch to get you into this theory you want to study? And there's basically two reasons for that. One is that in theories of the scale, in the early studies of the scalar part of the graviton, it was seen that there exist solutions, we don't know much about them, where this extra scalar can lead to the Hubble parameter being constant with nothing else in the universe. And so this is what's known as a self-accelerating solution. And so one of the potential ways to resolve the dark energy mystery is to say there's something in gravity that just makes gravity accelerate itself. And so this is a possibility. I'm not advocating for it. I'm just saying this is something that is possible. But the other thing that also appears in these theories generically is that if you have a graviton with a mass, then anytime you have a theory of a particle with a mass, then that theory can no longer realize the equivalence principle. So GR famously, we teach our high school students, I think, has equivalence principle. You can't tell the difference between sources of energy that is in GR. Everything from the cosmological constant to nil de Waal is treated the same like gravity. Gravity doesn't discriminate. Exactly. I mean, you're like right up there. You should have a separate slice on the pie charts of like baryons, dark matter, and but as soon as you have a mass, as soon as you introduce a new energy scale into a theory, then you can discriminate between sources of different wavelengths. In particular, the cosmological constant, or the dark energy, whatever it is, has a characteristic wavelength that is huge. It's infinite. For a cosmological constant, it's infinite. So the momentum associated with that is zero. So it's important. This is something that I also like to emphasize, is that the cosmological constant is often thought of as sort of like some problem that string theorists are going to take care of because it seems like a high energy physics problem. But the cosmological constant is the lowest energy physics problem in the universe. There is no lower energy scale by long leaps and bounds of orders of magnitude that we even have dreamed of measuring. It is the coldest physics that it can exist. So it's not, I mean, maybe it'll be resolved by high energy physics, but it would be kind of crazy if some low energy physics doesn't come into it. And so that's all just to say that having something, a low energy physics mass of the graviton, because the masses I'm going to be introducing are quite small, still allows you to treat the cosmological constant differently in gravity. And if you can, then what degravitation, the idea of degravitation is just basically that maybe it is that because the equivalence principle is violated, then maybe the cosmological constant has some big value, like the naive quantum field theory estimate would have. So, just the cosmological energy density is huge. It's some big number. But it doesn't matter because it's equal everywhere, and gravity doesn't see it very much. And so that's a thought. It hasn't been demonstrated it works. So, I'm happy for you to just take a wait and see attitude, but I just want you to know.
My favorite idea
what?
on this is that there is this huge reservoir of things that you don't tap into because of gradient.
There you go, from the mouth of the pond. So I find this to be a compelling idea as well. It hasn't been, so it can be made to work for very small cosmological constants. You can do it, but not for big ones yet. So getting it to a big one is going to be a problem. maybe, but it's something. Anyway, but back to my story. And so why did Pearson and Pauli throw out, or why was this massive gravity theory thrown out originally? So it turned out that, ironically, given that my talk's about gravitational lensing, it was gravitational lensing that threw out the theory in the first place. And why is that? So if you have a linearized theory with tensors and an extra scalar, the very most obvious thing that you do is that you change the way that gravity interacts between them. And so in GR, we know how strong the force is between me and you. And again, this is my favorite source of gravity in the room. And if you have an extra scalar, then that force has changed. It turns out that in these theories, that force, in the simple Pauli theory, that force is strengthened by a factor of a third. So gravity was 4/3 as strong. But in that linearized Pauli theory, gravitational lensing was unaffected because the scalar of the linearized theory didn't touch light rays at all. And so if you normalize the force g Newton by looking at forces, gravitational forces, then you have to ascribe 3/4 of g Newton to the tensors and 1/4 of g Newton to the scalar. But then the lensing force, or the lensing potential, is only the part that comes from the tensors. And so then you just have to do the comparison. So how big is the bending of light around the sun? Is it the same? Does that correspond to the same g Newton we measure on Earth, or not? And obviously, famously, one of the earliest confirmations of GR is that the light bending around the sun is dead on the GR prediction, right? And so that kills a linearized scalar right away, observationally. If you don't care about observation, it also was later proved by. So this is, I should say, has a famous name. This is the Van Dam-Veltman-Zakharov discontinuity. So it's a fancy name, VD-Z discontinuity, but it's basically the discontinuity's physical problem. So there's also another famous name associated with killing massive gravity, and that's the Boole desert ghost. So not only did the linearized theory of gravity, so the linearized theory of gravity had this problem. It turns out you can dress up the theory to solve the light bending problem by adding nonlinear interactions. So I mean, nobody thought that you should stop with linear theory and that's it. So the question is how you go to the nonlinear theory. And so Arkady Weinstein showed that you can go to if you nonlinearize it, then the light bending problem goes away because in nearby sources like the sun, it turns out the scalars sort of decouple from observation, so they don't play a big role, and so you can fix that up. But if you generically nonlinearly complete, if you just start writing down nonlinear terms for the scalar, then what happens is that what you find if you analyze those solutions is that there's not just one scalar anymore, that you end up picking up a second scalar field, and that scalar field is a ghost. So a ghost, like degree of freedom, I'll remind you, is something with negative kinetic energy. So which is basically this saying something that's highly unstable. So if you have a particle in your theory with negative kinetic energy, then it's always energetically favorable to create that particle. And since this particle will be part of gravity, it's coupled to everything. So it will kill you right away. I mean, you don't even get one step along if you have a ghost. You just die immediately. And so this Boole desert ghost, which is demonstrated to exist anytime you do a nonlinear completion of massive gravity with just generic parameters, then you're generically going to find a ghost. This led a lot of people to think that there's no reason to nonlinearly complete. There's no way to nonlinearly complete massive gravity. So that's where things rested for about something like 30 years. Until, from a very different direction, these guys came along and invented the Egp theory, which is, at first glance, nothing to do with massive gravity. So you've probably heard of this theory. So this is basically an idea about extra-dimensional gravity, where we lived on a 4-dimensional brane and there was an infinite extra dimension. And these guys found self-acceleration in this theory was one of the branches. It turned out this theory also had a ghost. And so I'm saying these words, self-acceleration, ghost, it's not by accident, it turns out, that the massive gravity story has ghosts and self-acceleration, and this has ghosts and self-acceleration, because as a 4D theory, it turns out you can write down the DG theory as a theory of massive gravity, where the mass of the graviton is not a hard mass, not like, so a hard mass is the masses that we're familiar with, where the mass doesn't change depending on what energy you observe it at, or ranges only weakly. But there's soft masses, or resonance masses, where the mass you measure depends on how energetic the experiment is. And so it turns out the mass of the effective graviton in GGP is in fact the soft mass. And so at first people thought that this is why at least part of the DGP theory got around the problems of massive gravity. And but it was very unclear at first. But the other thing that was uncovered in the studying of the DG theory was something about a Galilean symmetry. And so what a Galilean symmetry is something that was found in the equations of motion of the DGP theory. And it's basically that the scalar that was in the DGP theory was not, all the physics of the scalar associated with this DGP theory. I know this is a little bit abstract. I'm going to get to observations soon, so please don't let me lose you. Anyway, so this is sort of a cool point. That if you change the scalar by displacing it by a constant, or by boosting it, giving it a Galilean boost, so constant velocities in both space and time, that the physics were completely unchanged. And so that was the other interesting ingredient of the DGP theory. And this got people's minds working. And so just in the last year, Gregory Gavadadze and Claudio Duran have basically showed that if you're careful about how you do the nonlinear completion of gravity, it turns out that there is a unique, looks like a fairly unique way, it's probably not. I would say, what they would say is a unique way of doing a nonlinear completion of massive gravity that has no ghosts. And in that theory, what you get is a scalar just like you're supposed to. That scalar has this property. It has this Galilean shift symmetry just like the BGP theory did. And in that theory, you go from having a linearized, like a graviton with AQ nu, to a theory that has this interesting structure. So you have a scalar part, which is very familiar. This is just like how scalar parts to gravity have always been added. And then a new piece, which has to do with derivative couplings of the scalar. And so it's this interesting new piece that is the focus of my talk today. So how does that appear? And so just writing that out. Sorry? That's just the mass of the graviton. Oh, and that's going to be, or I'm going to associate with the length scale, which I'm going to call RC. Sorry, yeah, I never said this is the mass of the graviton.
Eta is the capacity.
Yes. Or just, yeah, this is the So I should say, so all of this is, it's hard to work with massive gravity, so right now you just look at perturbations on top of flat space. People have looked at it and they've constructed some exact solutions, like with consider asymptotic and Schwarzschild consider solutions in the theory. But for everything I'm going to talk about today, I'm just going to write down expansions around flat space and look at this.
I'm trying to understand the dimensions.
Yes.
H is dimensionless.
Yeah, the dimensions.
So pi is not like a scalar field. You've taken out some scales.
Yes.
And
I'm trying to write schematic rather than.
Okay. Well, anyway, but the non-schematic aspects are some interest presumably. So if you think about it as a classic scalar field, which maybe has a different set of interaction. So it's mg pi which is entering? Is that what is happening with that dimensionless form to modify the metric?
For this part?
Yeah.
So I think this is actually going to be implant.
Well, it's implant pi. Okay, so pi is have to be really and then there's an implant that's very
Yeah, there should be probably there's probably
okay.
Sorry. Yeah, sorry, what's the I don't think that my being consistent. Sorry about that. Anyway, so then the full metric then was something like this. And so this is where I'm going to tell you what my parameters are. So one of them is this crossover scale, what was called in the DGP theory the crossover scale. It was sort of the constant wavelength of the graviton. So wavelength associated with the graviton path. So that's I'm going to take that to be about the Hubble scale today. And then there's going to be two free parameters, A1 and A2. Turns out that in this nonlinear completion of massive gravity, you end up with some parametric freedom, and that's it. So there's going to be a lot of places where you could have as many as 5 free parameters, but there's only 2. So a total of 6 in principal free parameters, only 3 survive.
So what A1 something in the metric?
So A1 doesn't appear in the metric directly. So it depends. It comes into the coupling of the line, which I'm going to show on that side. Anyway, so the point of this talk really is to say that if you look at this, then always before, whenever people have studied theories of scalars plus gravity, you always have the extra scalar piece appearing the same way in the time-like and space-like parts of the metric. And what that means, and that comes from the fact that these scalars have always been coupled to the trace of stress energy. So you always write down something that looks like pi t, or where this is the stress energy tensor, and this is the scalar. And so radiation, of course, has no trace. And so these scalars never couple to radiation, so there's no effect on gravitational energy. However, whenever you have this derivative coupling, then that doesn't couple just to the trace, but it couples to the whole stress energy tensor. And so, in fact, you can have a modification to the lensing potential. And that modification, and so it turns out that the time derivatives of pi, you can just set to 0, or make very small. And then, so what you get is the lensing potential of GR plus a new piece, which we can then study.
So am I allowed to think of pi as an extra dimension with a specific form of the way it's coupling?
So there is a way.
I'm just looking at the form of the pi dot squared t squared di pi k pi. I think that's why it is pi times pi. And then I have an e to the pi ln pi as the overall conformal multiplier of the metric.
Right.
So it's sort of that from that thing. It's sort of like the ADS-CFT trick, except that there's a very specific form of what the work factor is.
I'd love it that way.
But I know it's a very good way to think about it like that. Because it's a nice way of encoding it. And you get the ability to do these pi surfaces as you approach the brain, whatever you want to call it.
Yeah, so there's no brains here, though.
The brain being just the limit of some limiting pi.
No, that's a good idea. In fact, the way that they originally figured this out, this completion, essentially is up because the first hints of doing this completion was to introduce a spurious extra dimension and then integrate it out. And they may have used the trick, so I can't remember now the details. They may have used some more trick. But to do that trick, you ended up putting in extrinsic curvature, but it was just like a DGP. By the way, this is the side of the side, so you can drop out if you're not interested in deep slopes. But in DGP, you have a R5 in the bulk. And so you have both full gravity in the 5 dimensions plus 4-dimensional gravity, and they interact. So to get this theory, actually, they just did the same thing, except for the 5-dimensional gravity is only extrinsic curvature, no inverted. And then
that would work too. Because pi would be like the spatial temporal hypersphere.
Yeah, so that's an interesting thought. Let's go thinking about more. Anyway. Right. Anyway, so, all right, well that's funny. But back to the main story. So it turns out that the equations of motion for this pi are intensely complicated, or in general. So that you have in general so equation of motion where you have second derivatives of pi raised to higher powers, more or less. It's the structure of the equation of motion. I decided not to write it down because it's ugly. But whenever the source for the pi field is spherically symmetric, then you get something that's like a Gauss's law, or it is a Gauss's law, I guess. So that you can integrate once, and you can reduce the differential equation for pi to an algebraic equation for pi prime, where pi prime is the radial derivative of pi, or the force of the unit of the pi field. And that algebraic equation is this. And so you see it's a cubic equation, so it's an exact solution, which I never learned in school, but it turns out that, so the cubic equation does have an exact solution. The general solution is kind of ugly and long, but there is one special case whenever the cubic equation has a very simple solution. And that is, given a cubic equation of this form, ax cubed plus bx squared plus dx equals b, and whenever 3 times b squared is equal to ac, then you get a simple solution. And it turns out, without doing anything, that the parameters of this theory are exactly the parameters that give you this simplification. So this a1 squared, a1, a2, a2, a combination exactly gives you the simple solution to the cubic equation, which is interesting. I don't know if it has any deeper meaning, but it's kind of cool. And so I should say, so whenever you do those solutions, it turns out that even though I wrote down this lambda 3 everywhere, the reason I haven't been dwelling on it, because in the actual solutions, the spherically symmetric things, lambda 3 never appears. Instead, what you get is a combination that gets called R star, or the Weinstein radius, after Arkady Weinstein. And so it turns out that the new scale of the problem for a spherically symmetric source, in the simplest case for a point source, is something like a geometric mean between the Schwarzschild radius, 2gm over c squared, times this characteristic radius of the graviton squared, all to the 1/3 power. So that's the number that comes in. So it's so even though RC, which is where you naively would think the new things would come in, like the Hubble scale, then for actual particular solutions, you get new physics that pops in at some parametrically smaller scale that's downweighted by the Schwarzschild radius of whatever the source of this field is. And so for the sun, it turns out this is like a kiloparsec. For a galaxy, it's like a megaparsec. And for a cluster of galaxies, it's like 10 megaparsecs. This is where the new physics pops up. And so the most obvious new physics is that the force of gravity is increased. And so you have an extra force in addition. So this is the Newtonian force. You have an extra force of gravity in addition to the Newtonian force. And that force is 0 for r equals 0, so that in the solar system there is no additional force. And then as you go out, as a function of r over r star, then you build up a new force. And so for this plot has been made for assuming a1 equals -1/2 and a2 equals 1/2, just for simplicity. And in that case, the form of this ratio is particularly simple up here. And so you can see the limits actually just by looking at this function. It's really kind of nice. And so for r equals 0, you have 0 plus 1 is 1. 1 to the 1/3 minus 0 is 1 times 0 is 0. So the force goes to 0 for r equals 0. And then as r goes to infinity, you have r over r star cubed plus 1 is, the 1 drop is negligible, so you get r cubed to the 1/3 r minus r, so that's canceled. And so you get the first term of the expansion, which is 1 over r squared. So you have 1 over r squared times r squared. And so times a factor of 1/3, it comes from the power here. So you have the strength of the new force compared to the Newtonian force is 1/3 times the Newtonian force. So that's the long-term asymptotic for the output. So you get a new force that's 1/3 as strong. And so this is the one that recovers the new force of the original mass of gravity. And so, but in general, this force can have any strength as long as you're willing to move up a1 up and down. So it's 1 over 6 times a1 in this way of parameter. So that's kind of nice. And so then you can just plug that into the lensing equation and ask what the fractional change in the lensing potential is as a function of r star. And so this is kind of nice. And so you get this simple form. And the ratio turns out that for a point source, that the size of the modification is a fixed number. So it's not dependent on any of the parameters. So the location is dependent on the other parameters, but the size of the modification is parameter independent, and it's this number. It's 1/12 times 2 times the square root of 3 minus 3, which is about 4%. And this peak happens somewhere around a little bit less than half of our star. So you modify the lensing potential by a fixed amount. And that's a prediction of the theory. So that's kind of nice. It's not something you can screw around with. But the location of this peak is, in fact, dependent on the parameters of the theory. So there's like this combination of A2 and A1. And obviously, it also depends on RC, because that sets the size scale of our star. So now, if you're a student and have thought about lensing, you know that the 3D lensing potential, which is what I plotted here, is not actually observable. You never see 3D lensing potential. So in a second, I'm going to actually plot what this does for an actual observable. But first, I'm just going to, because it's sort of a point of curiosity, so you can see that the modification, the fractional modification to dynamics and lensing is kind of like this. So the lensing modification is small and located around here, and the dynamics modification goes out to high radii. So they kind of overlap here. Which makes you think that if you ever really want to see this, you're going to have to understand both the dynamics and the lensing. But then, in turn, if you ever wanted to verify this theory, then you're going to be able to have two observations, in principle, two observations you can do. So you're going to see a modification to dynamics at longish length scales. And you're going to see a modification to lensing at fixed smaller length scales. So any questions at this point? Okay. So, now on to observation. So just my one slide review of weak lensing. So, as you can see, if R star for a galaxy is like a megaparsec, and if R star for a cluster is like 10 megaparsecs, then this lensing effect is going to show up in the weak lensing regime. It's really tiny down close where the strong lensing is king, and it's finite out here where there will probably be weak lensing. And so in weak lensing you have in lensing you have sort of two things to measure. There's convergence and then there's shear. And so it turns out that the thing that we're going to focus on is shear. And so again, for this A1 and A2 equals a half parameter set, you can just plot what the fractional change in the shear is versus GR as a function of R200, where R200 is the virial radius for dark matter gauge. And so what you find is this characteristic shape. Now, you'll notice that I haven't said what concentration of halo, or in fact, what virial mass I'm plotting. And that's because, basically, so I said that R star, so R star goes like the Schwarzschild radius of 1/3, right? But the Schwarzschild radius for a halo goes like the virial mass. And the virial mass goes like the virial radius cubed. So R star is going to go linearly with the virial radius of a halo. And so no matter how big or little your halo is, that as long as you measure in units of that virial radius, then the lensing effect will always appear at the same spot, more or less, up to a small variation. And so what that means is that you have a hope of actually detecting this effect, even though it's only a few percent. And so obviously, for this parameters combination, the only part that's sort of observable down here in the 1 to 2 virial radius range is this little dip. But whereas this big peak comes way out where the individual halos things are going to be hard to observe. But beyond that sort of observational question, the other question one might ask is, this is some characteristic shape, and one of the most obvious observational questions to ask about it is it distinctive compared with changes that you can make to the UNFW profile itself? So can it be mimicked by known physics, in other words? And so one easy way of seeing that it's going to be hard to mimic this with known physics is that the NFW profile goes like, so it's a characteristic density times a function of R with a scale radius in it. And so that scale radius is going to be parametrically smaller than the virial radius. So the virial radius and the scale radius are related by the concentration of the halo. Now the smallest concentration of any halo is around 4. And so at worst, at sort of the closest, your scale radius and your virial radius are going to get a factor of 4 off. And in general, they're going to be much further apart. So that's why whenever you change the mass of the halo, then what you find is that the change of the shear kind of has a shape like this. And so you can see it sort of has a lot of change down here, which is around the scale radius. And then a smooth scale, then a smooth tapering off at high radii. And if you change the concentration, it's sort of a similar story. So it's going to be very hard to get anything that has this characteristic shape, because the structural sort of the functional radius, or the new scale of the modified gravity effect is around the virial radius, more or less. Whereas the functional scale of anything about changing the NFW profile itself is going to be like the scale radius. Now you can move away from the NFW profile and possibly get some other effects, and we're looking into that now. And the other thing you might worry about, given what I showed earlier about the change in dynamics, is that if you have a modification to gravity, then the NFW profile itself might be modified. So that's something that Neil and I are actually working on, part of why I'm here, is to actually try to understand what halos will look like if you have an extra force playing this kind of role, just so we can see if we can disentangle that effect as well. But so that's the sort of basic story. But just for interest, I wanted to show you that you can get very different. You can move things around quite a bit just by parameter choices. So if you go from, instead of the one half choice in before, you choose A1 as a -1 and A2 as an 8. So not that radically different. And you can basically move these effects into much smaller radii. And you get a change in the shear that sort of has a lot of support. It changes a lot sort of around the 1 virial radius. So those of you maybe who don't work on these kind of observations, so 1 virial radius is kind of the boundary between what's easily observable and what's going to be hard to observe because of complications from other halos. And so you're pretty sure that down here you can do observations and get reliable results for Wyman, whereas out at like 5 or 10 virial radii is pretty hopeless. So that's why it's interesting to know if you can move the effect into low radii. And so again, it's kind of hard to. But the only problem with that is that as you move it in, then you could have a danger of having the effect look a little bit like modifications to parameters of the NFW profile itself. So again, so this is something that's going to require careful study to disentangle whether you can really see this or not. And so I guess the last thing I have to say is just to tell you, I've been showing plots with percents on them here, and you might wonder if it would be ever possible for a weak-limiting experiment to actually see this. And so I'll argue very briefly that it is possible by doing a very simple signal-to-noise estimation. So basically say that our signal is going to be a change of the shear on top of the GR shear divided by the noise intrinsic to weak-limiting observations. And so it turns out that noise is about 0.3 per galaxy observed, and then you just beat it down with statistics for a minute. And so since the GR shear on these radii is like 1%, and the modification is like 1%, what you'll need is like 10 to the 7 observations to have a chance of getting signal to noise greater than 1. So that seems like a big number, 10 to the 7 observations. But it's actually not that big. And the reason why is that as I explained, this is the effect shows up at the same radii, the same scale radial location for all halos. And so what you really need is just 10 to the 7 total observations on any halo. And there's already that many halos that are observed doing something in the longitudinal step survey, right? Sort of order 2 to 6.
The signal to noise measured per shear is better than the ones that you do that.
Yeah, so it's not crazy to get this. And just as an example, so for the Large Synoptic Survey Telescope, they claim they can get 40 galaxies per arc minute whenever they do the observation. And so then if you just take fiducial value of 5 arc limits subtended by each lens in the sky, then you just need just 50,000 lensing halos to get enough statistics to detect a 1% systematic effect. So that's just really ballpark numbers, but this is to say it's not crazy. So, so that's actually all of the material I have that I need prepared. So I'm happy to take more questions.
Can we go back to just something trivial, but my mind was wandering into the extra dimension. Just the basic equation for pi and how it's responding to rho.
Yeah, sure. You mean the spherical expression?
But that's fine. Okay.
I write down the whole thing if you want.
Well, first of all, there are pi waves. Are they of any interest?
Maybe. So because the coupling is suppressed for near sources, they may not be then included. I haven't really been calculating very much.
Okay. And so the other issue is that, so my understanding is that at least within these spherical models, you're saying that the strength of gravity is diminished in some controlled way. What's the impact of that for the ISW effect?
So because it always goes, for ISW there won't be any. For ISW it's changed, so the ISW effect is changed only if it's changing in time, right? Not if it's changing on space.
Well, except that this, well, maybe I'm wrong. It could be. I'm just thinking that what we're talking about is that there is a characteristic scale at which the gravity changes, and building that characteristic scale in may have an effect of temporal relation as well as positional, just because there's a radial direction associated with time.
Yeah. I mean, as something would change as the light ray goes in and out. I think that the effect is changing slowly enough relative to that it's actually not going to make too much of a difference. Okay. But I should say there is another effect, which is that because gravity is stronger, so the infall. So basically the time at which infall winds versus dark energy changes. Yeah. So that does show up.
And that actually would be really interesting to see if that sort of thing has impact on clusterology, not the lensing, just sort of. I mean, maybe it's just too subtle to see.
You have to. People have studied that. So basically, the point is that one of the things we observe is just the fact that as dark energy turns on, the clusters are growing before that, and as dark energy turns on, because it's a repulsive force, the clusters stop growing, or at some characteristic scale, the structure stops growing and starts shrinking, or starts dissipating. And so you can see that change from growing to dissipating in C and B observations. And so the strength of gravity actually comes into that, telling you when we switch from whenever the overall accelerating expansion starts to beat the infall strength of gravity. And so that has been calculated, and I think that it's unobservably small if you modify gravity at sort of this, even a third, like a quarter, like a third level. I think you have to make a bigger change than that, but I can't really remember. But it has been calculated.
Right.
I just can't remember.
And so the other intriguing thing is that, but you didn't come back to it, which is soft mass compared to hard mass. Soft mass means running mass, presumably.
Right. These are hard masses now.
These are hard masses. I see. So it doesn't. I was just intrigued by wanting it to be 1 over h.
Right.
And therefore, h broadens, and therefore, like when I mean, you're doing that m is of order h inverse because you're saying that's what you need.
Right. But there's no reason that's
But
the theory
it
doesn't
would
require
be
that.
nice if there was a relation. I don't know.
No, it's possible. Yeah. I mean, the theory is not complete. So I mean, that was one of the not sure how the masses would be really normalized. The mass of the graviton not itself would be really normalized.
So the self-interaction is in this theory.
So the interaction scale is, I think, subject to something. I think that people have claimed that it's subject to a non-renormalization, but they're non-renormalizable interactions. And so, but because of this Galilean Cemetery, I think you can argue that you won't actually get renormalized. You really want to renormalize it.
How about the interaction of the scalar, for example, with other particles?
You mean what
Those
was it?
have to be normalized. Oh, yeah.
You mean
For example, or something like that.
Like the lambda 3 scale itself, whether that's going to be renormalized through interaction.
So when you have this theory interacting with masses that aren't part of this theory, absolutely you'll have to normalize.
Right, you do have to think about it. So it's a little tricky because of the symmetries of this theory limit what kind of renormalization, what kind of sort of imperfection exists on the phi itself. Which some people, the claim has been made that the theory is is not subject to renormalization as a result of this. But I myself have investigated that pretty much. But this is definitely something to think about and be concerned about.
But there's going to be some kind of renormalization. It's just a question of whether it's the coupling or it's actually the NP, because everything is renormalized.
No, sure, yeah.
Okay,
Right, yeah.
Yeah, so sure. Right. That's the thing.
Yeah, I don't think that that's really exploited at all. I mean, it's the only kind of shows that the theory didn't have. You could construct a version that didn't have ghosts, like even classical ghosts, like in the last year. So I haven't quite gotten to the full like renormalization. No, but it's definitely important. Worry about. Other questions? Observational questions? Basic questions? I left lots of time.
Well, I guess maybe a definitive statement of is this dark energy?
Ask me again when we do.
Okay. Well, it's being introduced because you want to modify, but is it far enough advanced to be considered to be a solution?
No, I would say not.
So these theories have to put in lambda by hand also, I thought, right?
So, well, at the moment, yeah. Just because, but that's the main issue because we're not really well.
Yeah, I mean, you could imagine a scenario where this kind of thing, I mean, if what I was saying with the d pi squared is an extra dimension with the conformal factor, it has maybe something in common with the f of r tendency, and if you get a little more complicated, you want to be able to fit those in.
Yeah, where you just have a character to scale where things.
Yeah, although, you know, solving all problems simultaneously would be awkward.
You never know.
You never know. Like you go over the head.
Yeah. Other questions?
Thanks again, Mark.